Hi there. Thanks for listening in to 2014 MCU Deep Dive. My name is William Go. I am with the MSP430 applications team here based out in Dallas. And today I am going to talk about Energy Trace++. I'm going to go into the details of what it is and how that benefits you. And then we're going to do the hands-on portion of it after that. So before we get started, I want everyone to make sure that they have the proper environment set up. In our case, we're going to be using Code Composer Studio 6.0 here. And you can actually download it from www.ti.com/ccs. That's the first thing. The second thing is you have to make sure that you get the right EVM. In our case, we're going to be using the MSP-430 FR5969 Launchpad, as you can see here in this image here. One key thing to note, make sure that you have revision F silicon on there before you get started also. So the revision F should be printed on the circuit right there where my mouse is located. The next thing is you're going to obtain the lab files. The lab files should be available to you in the folder or wherever you're downloading it from. And then you're going to create a new workspace, and then you're going to copy that project into your workspace. So today's agenda is going to be pretty, it's going to be stretched for 2 hours. And first, I will introduce you guys to Energy Trace technology. I'm going to talk about what it is and how it works. And then I'll discuss about the available hardware support for Energy Trace and also the performance for Energy Trace. Next, we'll get some hands-on experience with Energy Trace tool as we walk through together to learn how to use each feature in Energy Trace itself. And then after that, we'll build upon the second section, which is the hands-on portion. This is where I want everyone in the room to be to use ULP Advisor, look at the advice on there, and try to optimize or improve or fix that ULP advisory, and see with your own eyes how that can translate to energy saving in Energy Trace. So of course, the next thing is I want to show you guys is a little bit on how to do absolute power measurements with this Energy Trace. So we're going to do a hands-on portion of that too. And then after that, we'll close out with a short summary of what we captured for the whole entire session. So the motivation behind creating an energy-aware software development is to solve a very basic energy equation, where energy is related to current times voltage, which is equivalent to power consumption over time. Every battery has one thing in common: finite amount of energy, right? So in a runtime environment, the performance requirement and power is the energy consumption over time. Depending on the capacity of your battery, this determines the lifetime of your application. So software development with energy awareness in mind is based on finding and optimizing every part of your software that consumes the highest energy consumption. This can be identified by identifying power-hungry peripherals or external hardware that is, that should be turned off at the necessary time, and trying to detect any kind of unexpected power peaks in your code, in your software. And then of course, you want to make sure you check and see that you're using the right power saving modes for your application also. So what tools would I need as an embedded engineer to accomplish this goal of analyzing my energy consumption? I mean, you as a software developer will most likely resort to these few equipments that you will see here on the bottom left corner. You probably need some kind of multimeter. If you want to do a current profiling, generally you will need a shunt resistor on there, hooking it up to the scope and look at your power consumption and the necessary FET programmer, the target boards. Now this is a pretty daunting task to go through just to identify how much power consumption that I've used in my system. Well, you can put those debugging days behind you. Now we have Energy Trace Tech++ technology. It's a new and powerful tool that MSP430 just released. This complete tool measures and records energy, power, CPU, and peripheral states over time from one single tool. As you can see here, I have states, I have power consumption, and I can see that over time. And all of this is completely integrated into Code Composer Studio and also in our IAR environment. So these snapshots here you'll see are all completely integrated into CCS here. And we're going to be using CCS in our lab today. So I could essentially accomplish all of the MSP430 debugging capabilities with this IDE environment plus more, because I can actually see what my CPU and peripheral states are doing as the code is executed in real time. I could quickly identify areas of energy inefficiencies in my code by observing peripheral states being activated when it should not be activated. So this is not just a simple multimeter here. This is a current profiler in your pocket that offers high dynamic range, which is capable of measuring from hundreds of nanoamps to milliamps of current. You can now spend less time debugging your application and spend more time developing by using this tool in a single tool here called the MSP430. So MSP430 here supports both the power analysis and also it can program and debug your application at the same time. There are two terminologies here that I really want to make everyone to be aware of. The first one is the energy trace technology. The next item is the energy trace plus technology here. Energy trace portion of the energy trace technology allows you to measure current or monitor the current, and it is supported by all MSP430s. Now on the energy trace it is currently supported by all MSP430 FR59 and 69XX family of devices. And the reason being is because to enable this energy trace technology, you need special debug logic to be in the circuit to be able to transmit all of this great information, which is like the CPU states, the peripheral states information, back to the PC and display it on your IDE environment here. So there are three components to enabling energy trace First, you need the device. For some devices in the MSP430 portfolio, for example, the MSP430 FR58 or the 59 or the 69XX devices, these devices have special logic in there, like I was mentioning in the previous slide, will provide you digital state information back to the PC. Then there's the energy consumption portion of it. The energy consumption portion of it is supported by all MSP430. And then the second part is you need to have the right emulator or the hardware to enable energy trace. There is the MSP430 or the EasyFET onboard emulators, which are generally available on the launch pads. And then last but not least is you need the IDE support to display all of this information. In this case here, for example, in CCS, you have CCS and also IAR graphical environment here. This is a TI patented technology which allows very accurate energy measurements by using a novel method of digitally counting pulses. Each generated pulse is a known amount of energy that is fed into the system and then accumulated to sum the energy consumed. As you will observe here, the higher the system consumption, the higher frequency the pulses are. And the system knows how much energy it is sent into the system through each and every single pulse here. There is no shunt resistors involved, and so there's no any form of or sampling frequency of the voltage of the shunt resistor. What I want to say is that this is beyond current measurement. In the MSP430 FR59 and 69 devices, you can capture peripheral and also the CPU states as you can see here. LPM2, back to active mode when it wakes up, and then goes back to sleep here in LPM2 here. And then during active, I can see the FRAM access, the timer is going off, the M clock, SM clock is activated during that period of time. And all of this information are read behind the scenes through the emulator, including the low power modes. So you don't have to do anything. However, Just be aware of some limitation to this tool. Not all states can be captured as some of these transitions happen so fast and so quick, like for example an ADC conversion. The Easy FET is the cheapest solution to get started with energy trace. This is the successor to EZ430. This is a complete in-system programming and debugging tool which supports any MSP430 using SPI-by-wire interface. It has energy trace technology on board that is capable of sampling or grabbing data at about a rate of 1 kilohertz. It comes with an improved backchannel UART, where now it supports UART communication up to 56 kilobits per second, instead of before where it's fixed to 9600 baud rate. It is also field updatable, unlike before. And it does come with only a fixed 3.6 volt supply, which can handle up to 75 milliamps of current. Now, on the other hand, the MSP FET, this was just recently launched. This is a new tool which will program all MSP430 devices. This is a direct replacement to our previous generation MSP430 FET 430 UIF tool. So it has a USB debug interface that programs any MSP430 that uses 4-wire JTAG or the 2-wire SPI-by-wire mode. It does include energy trace technology, just like the Easy FET. This tool is 4 times faster than its predecessor, and it includes now a backchannel UART also, just like the Easy FET. And this thing will operate up to 56 kilobits per second. This is also field updatable. Just like our previous generation programmer, it supports programmable voltage between 1.8 volts to 3.6 volts with 100 milliamp overcurrent protection. It supports JTAG security fuse blow. And also keep in mind, this tool here has a higher resolution than the Easy FET when it comes to the energy trace portion of it, the sample rate, basically. And of course, coming soon, which this tool will support BSL programming modes in the future. So this tool is orderable now. It's in our e-store, and you can follow this link here, www.ti.com/tool/MSP-FET. I want everyone here to have a few key takeaways from today's session and have certain level of expectations towards energy trace. Plain and simple, energy trace measures energy. The accuracy, even the smallest events are captured. Do keep in mind that this tool measures energy and the current is derived from energy over time. So with that, please have the expectation that averaging is done to avoid noisy current or power graph. When there are lower current draw, the results are lower update because less charge pulses are needed. It, however, does not affect the accuracy of the energy measurement. Also keep in mind that energy trace requires debug communication to transfer CPU or peripheral states information back, and this can add into your energy consumption of your system. So if you look at this graph here, in the energy trace mode, which is where you just measure current only, if you just click resume in CCS, which is the play button, this includes all the debug communication. Basically, the device is actively communicating to the programmer so that it can poll for any kind of breakpoints that gets hit and so forth. So this applies to all MSP430, including the FR58 and FR59 device. Now, if you set CCS 6 to do a free run mode, all of the JTAG pins and the SPI-by-wire pins are basically set to high Z. So this this will disable all the debug communication, and this is more like a standalone, like energy consumption can be done that way. Now, on the other hand, on the energy trace plus, of course, you will see an X across here. The MSP430, FR58 and FR59 is supported here. So if you click resume here, this includes all the debug communication, all the digital state are read back basically. Now, on the other hand, in the free run mode, this is not supported because if you think about it, Energy Trace++ needs to be able to send all of this digital state information back to the PC. If it is not, then might as well you set it to the energy trace mode, and you can do your current measurement that way. Last but not least, I wanted to have one more key takeaway for everyone here is that Energy Trace++ is not a high-speed digital trace. Typical speed is between 1 kilohertz to 4 kilohertz, depending on the debug probe hardware and the debug protocol settings also. So getting started with Energy Trace is an inexpensive price tag. With this bundle here, starting at $29.99, you can start with the Launchpad that has the MSP430 FR5969 device on it, plus an LCD screen. So this is what we call a bundle pricing. And you can order it online here from ti.com/tool/MSP bundle with this link. So this slide here just kind of, I just want to quickly highlight that we actually have an application note that we just recently published that talks about Energy Trace and also ULP Advisor and how you can use ULP Advisor with Energy Trace to optimize your energy consumption of your system here. So with that in mind, we're going to go to the next section of the class here, which is the hands-on portion of the Energy Trace technology. And I want everyone to be familiar with the tool. So the goal here is pretty simple. I want everyone to get your feet wet. I want every attendee in this room here to walk through this next few clicks on how to use Energy Trace with me. And the handouts are in front of you, which you can use to also follow along. If you need to go through the handouts, it is slide number 16. Let's get started with the lab here. In my case here, I have a brand new workspace and I have already successfully imported a project into my workspace. So Energy Trace is not enabled by default in Code Composer Studio 6.0. So to enable it, first, I want you guys to go to Windows, Preferences, then pull down Code Composer Studio, go to Advanced Tools, click on Energy Trace Technology. I want you to check Enable. This enables Energy Trace Technology for the lab and also for the workspace. And then we're going to go with Energy Trace++ here. Click OK. The next step here is to ensure your low power debug mode is enabled. So this is usually enabled by default. This is just a quick check. Make sure that it is checked. This is very important to enable Energy Trace. So you right click on the project, go to Properties, go to Debug, go to MSP430 Properties, scroll down, and make sure that this box here is checked that says Enable Ultra Low Power Debug in LPM X.5. Click OK. All right, the next step is to check and see you have the Inefficient project selected. So if you right click on it, go to Build Configuration, Set Active, make sure you're inefficient. We're going to start off with that. We're going to start off with the most inefficient project and we're going to measure the energy consumption for that. Okay? Next step is I want you guys to build a project. On the top right corner here, you will see a tool that says Build Inefficient Project. Click on that. I'm going to let it build right through it. I'm going to close this getting started. All right, so this is success. A successful build. And now we're going to drill down into this Power ULP advice here. One thing you'll realize in this application here is that it used a lot of inefficient programming method for an ultra low power application. And the power of ULP advisor here is it's able to catch all of this and inform you as a software developer that, hey, you need to start looking at them and address them. And you can click on every single rule here and it will navigate you to what the rule is. And it will tell you what it means, the risk, you know, why it is, and how to remedy it. And then we have code examples to show you how to fix it. So the next step is I want everyone to make sure to prepare your hardware. If you look at your launch pad in front of you, I want everyone to make sure you remove the CTS, the RTS, the RXD, and TXD pins, and they are all located on J13 jumpers. These are not needed for our project. So the next step is I want you guys to download and debug the application. So we're going to click on this little bug icon here. You will get this ULP advice screen here. This screen will come out if you have a ULP advisory in your project. So in our case here, we're going to ignore it, and I want everyone to click proceed for now. All right, this is a successful download. Next step is I want everyone to go to line 110, and I want everyone to set a breakpoint right there. To set a breakpoint, you can either double click here on the left side of this blue color bar where my mouse is, or you can right click on it and you can go breakpoints and you can set hardware breakpoints or breakpoint. So we just set a breakpoint there. I want you all to run to the breakpoint first. Once it reaches that breakpoint, and then I want you guys to go to energy trace view, which is going to come up by default on the bottom right corner of your screen here. Just quickly double check, make sure the measurement duration is at 10 seconds. So you can actually configure the measurement duration here between 1 second, 5 seconds, 10 seconds, 30 seconds, minute to 5 minutes here. So you can choose the different capture time frame. In our example, we're going to be using 10 seconds, and then just run. When you click run or resume in this case here, energy trace is going to start capturing for the next 10 seconds, which is the duration that you have set. So the first view here is the energy trace view. You will see all of the functions that you have in your system and what was the percentage runtime and what's the percentage energy that's being used by the system here. So you'll see, like for example, the mem set, string length, basically these are all your functions that are in your application here. And then if you scroll to the bottom, it'll tell you what's the percentage of the runtime for your peripherals also. It's a very, very powerful tool to quickly identify problematic areas. I mean, I just realized that, hey, you know what? My program is 100% active. I am not using a single low power mode here. And then of course you can see also the power consumption of the system also. Now one thing I want to bring you guys to be aware of is there are no absolute power numbers here. So in the Energy Trace plus mode, I was showing you guys earlier a comparison chart that debug communication affects energy measurements. So in this case here, since in the Energy Trace plus mode, it needs to send a bunch of data back to the PC, the debug communication layer is always going to be active, and that will skew what your energy consumption of your system is. So in our case here, what we're going to do is we're going to just not show you what the absolute power number is, but what I'm going to show you after this is how you can compare between two different current profiles before and after to showcase that by you improving your code for energy efficiency, you have successfully seen a decrease in current consumption or increase in current consumption. The energy graph Same thing, no absolute power numbers or no absolute energy numbers here. And then I want to show you guys the states. This shows the 10-second runtime here, and within the 10-second, my application wakes up every second periodically to transmit some data packets out through the ADC to the USKI or UR communication. You will see that the ADC kicked off here. Some ADC kicked off some sample here, and the timer is the one that kicks the ADC to start sampling. So you see that my application is in active mode the whole entire time. FRAM is running. This is basically the worst possible scenario for an application that is not low power at all. Now I do want to keep a certain level of expectation that Energy Trace++ may not be able to capture all of the states if the state transition is too fast. In this case here, let's think about it like, for example, the ADC. The ADC is only on for a very, very short period of time, and with this easy FET here, there are small possibility and chances that it may not be able to capture the state of the ADC, but the ADC actually in actuality being kicked off and executed here also. So by it not being displayed here, it does not mean that the ADC did not run. Now, of course, if you use an MSP430, which has a higher resolution sample rate, you will see all of this in there. So if you see in the slides, number 28, you will see that the MSP430 is actually capable of measuring and capturing a 4 kHz, so you see all of the state transitions perfectly. So go back to the Energy Trace Technology tab here, and I want you guys to save this profile. So to save the profile, you see the Save Energy Profile. Click on that. I'm gonna call this thing as Inefficient. All right, done. Now, we can terminate the debug session. Next thing I want you guys to do is switch to the most efficient build configuration now. So if you go right click on the project, go to build configuration, set active, and click on most efficient. So what this project does is that we have successfully gone through every single UOP advice and improve the project for you, so that in the essence of time here for this class and this lab here, we've actually done it for you, so that it kind of gives you the idea that we have gone through every single line of code, improve it based on the UOP advice, and we're going to observe how much we actually have improved. So I want everyone to build your project again. One thing you'll realize is that, wow, if you remember correctly, before that, there were several UOP advice on there. Now we just have one of them left. So we have gone through and addressed every single one of them. And let's see how much that improves. So I want everyone to go and download and debug this application now. We're going to click proceed here. All right, next thing is I want you guys to set a breakpoint at line 131. We're gonna run to the breakpoint first. Now, as soon as I click resume here, this is where the Energy Trace++ will start capturing all this data and information for the next 10 seconds. Done. So if you look at this profile here, we've successfully used or turned on at least a low power mode Even with the low power mode here, we're 85.2% on all the time, and we're spending about 14.8% of the time in active mode here. So you'll see that my timer is always on, my reference is always on, and my A clock is on, which is what I expect it to be in LPM3 mode. So the M clock is the one that's on at 14.8% of the time, which is where it means the CPU is active at that point in time. And this should be aligned with the active mode. So if you look at the power consumption here, there's still no absolute power numbers here, but I don't know how much my energy has improved yet, right? Well, let's get back to that in a little bit. So same case with the energy, no absolute power energy numbers here. Now, if you look at the states here, this is kind of interesting, right? This is how a typical ultra low power application should look like, where you're in sleep as long as possible, you wake up periodically, you execute your code as fast as possible and go back to sleep. So you see that during this active period of time, my FRAM is activated, my ADC is running, my M clock is running at that period in time, and my A clock is always on because of my timer. All right, so let's go back to the energy trace tab technology here. I want everyone to save this current profile. All right, let's save it as most efficient profile. Okay. Now here comes the fun part. So in this energy trace tab here again, I want to load a reference profile now. So what this load does is that I want to compare my current profile with my previous profile. Let's compare my most efficient profile with the inefficient profile. I want everyone to select inefficient.profile and click open. This is now more meaningful. So if you remember correctly, our most efficient code was an improvement on top of the efficient code. We didn't change the functionality, we just changed the behavior of the system to use low power modes, going to sleep, not using printfs and so forth. So you will see here that a comparison of how much of the system is in LPM versus active mode. I can look at the comparison here, the delta. And what's more interesting is if you click on the power tab here, this was my inefficient code right there. And this is now my new most efficient code. So this is the relative graph or power consumption of how much your system has improved from before to after you optimize your system. Same case with energy. This was my inefficient energy and this is my efficient energy. I have successfully reduced this amount of energy here. Now, however, there's no comparison for states. So now I want everyone to stop the debug session. Now that we have familiarized ourselves to energy trace, I want everyone now to do a little exercise on your own, which leverages ULP Advisor to optimize your energy consumption while using energy trace. Just now earlier is that there was one ULP advice remaining in your system. There was an uninitialized port B in your project. I want everyone in this goal, the goal here is that I want everyone to fix that one ULP advice in your project, and then I want you to go build it, download it, and debug that project, and I want you to save the profile as the most efficient solution profile, and then I want you guys to compare between what you just fixed with the most efficient profile before. So I want to see if there's a energy gain by fixing this last piece of UOP advice there. So let's spend approximately 15 minutes on this lab here. To fix this UOP advice, going to be the following here, and I'm going to go through this whole entire exercise here. So if you go to the most efficient here, it says port B is not initialized to be an output port pin. So we're going to do this, port B dir equals to 0xFFFF. So what we're doing is we're initializing all of the port B pins, port pins, to be an output direction pins. And if you see PB out here, we're setting all the output port pins to be low voltage level. We're going to build a project. And voila, we've successfully cleaned out all of the UOP advice here. We're going to download this project now. So remember to set the breakpoint where it says set breakpoint here. So in our case, the breakpoints are already set. We're going to click run. And then we're going to run from the breakpoint now, so that energy trace can start capturing for the next 10 seconds. All right, so energy trace plus plus is done here. This tells me that the system spends about 85.2% in low power mode and 14.8% in active mode. So the power numbers, the percentage runtime is exactly the same as before, and my power profile and so forth. Now I don't know exactly how much power savings I've gotten here by improving my code. So what I can do here is, if I go back to the energy trace tab technology, I can click save current profile. First, I want to save this whole entire profile. I want to call it most efficient solution. Okay, now click save, and then we're going to go back here and we're going to go and load the profile from the most efficient. We're going to compare how it looked from before. So the yellow is our most efficient code earlier. And this is showing us the relative amount of energy that we have successfully squeezed out from the system by simply just putting one line of code and following the UOP advice here. Same goes with the energy. So if you look at this energy trace tab technology here, what you see here is that the delta runtime is almost 0% here. There's no change, nothing at all. It's just the energy consumption has decreased by almost 37%. That's a big number. So in the next section here, I want to show you guys on how to do an absolute power measurement, and this can be applied to all MSP430s. So if you saw earlier in the hands-on portion for the Energy Trace Plus technology, we were measuring everything with relative power numbers. So I want to see some real power numbers as to what my system is actually consuming now. So I want everyone to walk through with me also, same like before, and I want everyone to be familiar with all of the settings and where things are and how to get to energy trace mode. All right, so if you are still in this energy trace view here, and you're still in debug session, which we still are, we haven't terminated the debug session. Now, if you have accidentally terminated your debug session, you can always re-enter back the debug session by clicking the bug icon here. So, we're still in Energy Trace ++ mode here. Now, to switch to Energy Trace mode, there's a quick and easy way on this toolbar here. So, if you put your mouse right under here, on the right corner of the tabs here, you will see that says switch to Energy Trace. So I want everyone to click on that button. And you will see that the view for Energy Trace has changed. I no longer have the States tab. My energy view now has numbers on there. Same with my power. And if you click on Energy Trace tab here, it's completely different. It's telling me time, how much energy is being used, power, voltage, and current. So I want everyone to pause your application for now. Just suspend it. And if you remember correctly, in the first few slides, the debug communication layer affects the power consumption, right? So, but if you do this in free run mode, it puts all of the JTAG pins into a high Z state. So in our case, if you go click on run, and then click on free run. So you go free run, this puts all the pins into, all the JTAG pins into high Z state, and we can start capturing energy in a more absolute fashion and also more accurate power number. So this thing just ran through 10 seconds. This thing is telling me that my system consumed about 1.46 millijoules in 10 seconds. Average current is about 50 microamps. So if you click on power here, you will see a lot of state transitions here. So like I was mentioning earlier, there's a lot of averaging that goes on in this power graph here. So this thing, and also I was mentioning that power is derived from how much energy is being consumed. So the smaller the current, the transitions are a little bit less frequent, hence you will see a lot of more averaging that happens here. So if you have a higher current system, you will see a better resolution power graph on your system. But this tells me at least, hey, you know what, this is how much my system is consuming here, and so is my energy consumption also as it goes up. All right. In summary, there are only 3 major energy trace windows here. In the energy trace mode, this is where you measure absolute power numbers, absolute energy numbers. So we have the power, we have the energy, and we have the profile view. And all of these are available with MSP430 devices when you use it with an MSP-FET debug probe, or if you have the EasyFET here. Now on the Energy Trace ++, you actually get more views here. You'll get a profile, you get states information, you get power, you get energy also. And this is available to only MSP430 FR58, 59, and 69 devices. So with that, I want to show you guys the key takeaways from before. And I hope by now that everyone in the audience here has gone through the whole entire lab session, knowing how to use Energy Trace and how to use that and leverage that for your application. So let's quickly go through this slide again. Energy Trace strictly measures energy. Even the smallest events are captured, right? So you guys saw earlier in the previous slide on the absolute current measurement how the energy, the current consumption doesn't look as pretty because we're actually operating at a very low current. So at a lower current, is trying to, it does a lot more averaging from the amount of energy that's been consumed. And how we did that in a free run mode also is because we don't want any debug communication to affect our current reading here. That's for the energy trace mode. And then if you remember correctly, in the energy trace plus mode, that's where it includes all the debug communication layer, where it sends all the CPU and the peripheral states information back to you, to the PC. And in the energy trace plus mode, it doesn't support the free run portion of it. So for the free run, always switch back to the energy trace mode and use that way. All right, so one last thing I do want to mention is keep in mind energy trace plus is not a high-speed digital trace. Like I was mentioning, the typical sample rate is between 1 kilohertz to 4 kilohertz. And you know, we've seen that instance where the ADC wasn't showing up because it happened so fast of the transition that the EasyFET wouldn't capture it. Now, of course, if you use the MSP430, it will most likely catch that because the MSP430 has a much higher sampling rate on the energy trace compared to the EasyFET here. So with that in mind, I would like to actually thank everyone for attending and listening in.